Muted.
11:04. Yeah. Mute only. Yeah.
So, welcome everybody. Morning, we are now live. So the second day of today's second day of the Science Day program of the University of Astrophysics. My name is
Neeraj, you're muted.
Oh, I'm sorry. Yeah. So good morning, everybody. Welcome to the second day of the National Science Day celebrations of the Indian Institute of Astrophysics. I'm Neeraj, and I'm here with Crispin from the outreach section of the institute. So today is the second public talk of 4, which we'll be doing over yesterday, today, and tomorrow. And the topic of this talk is something I guess everybody has been interested in forever and ever. It is about life elsewhere, right? SETI, extraterrestrials, UFOs, or what have you. So this is something which for a long time has been a part of science fiction or conspiracies. But we are fast, but now we're in the era where this is no longer science fiction, but proper hard science, right? And today's talk will be about how the search for extraterrestrial intelligence has become hard science, and how scientists can collaborate in this venture and do something which is much more rigorous than what is done before. And what can we do in the future, right? So the speaker today is Vishal Gajjar, who did his PhD in NCRA. You can see the GMR telescope behind him. This is when I knew him when I was working there. So Vishal Gajjar got his PhD from NCRA TIFR, and his thesis was on radio pulsars. And then 2016, he joined UC Berkeley as a Templeton postdoctoral fellow, where he led the design and commissioning of a fully commensal real-time fast radio burst detection system. These are very transients whose origin is still relatively unknown. And he built this for the world's biggest telescope, which is the FAST telescope in China. And he also led the first and so far the only detection of fast radio bursts above 5 gigahertz, and first reported detection of a fast radio burst from GMRT at the lower radio frequencies, right? But then, as he said, as he told me, to quote him, since my childhood days, I was curious about the existence of extraterrestrial life, and Breakthrough Listen is probably humanity's biggest effort to answer this question, and I'm thrilled to be a part of that. And motivated by this, he's now an academic researcher in the Breakthrough Listen team at University of California, Berkeley in the US. He's the project scientist for the Breakthrough Listen's international facilities, and he collaborates and enables SETI-related activities among half a dozen observatories around the world. So we talked to Vishal Gajjar from Breakthrough Listen, UC Berkeley. Will now talk to us about Breakthrough Listen's search for the evidence of intelligent life. So Vishal, please go ahead.
Thank you, Neeraj. Thank you for that kind introduction. Let me share my screen. It's all good?
Yes.
Okay. All right. So thank you for inviting me to kind of give this talk. I'm thrilled to basically talk to you all about our recent project. It's at 6 years old, so I can still call it recent. The program name is Breakthrough Listen. So my goal for this talk will be to give you an outline. Obviously, it's very hard in an hour to give you a full flavor of everything that's been happening in the group. But at least I'll try to give you various different aspects of what are the progresses that we've been making about how to answer this question. So to start with, when you look at the stars, like when you look at the night sky, we see large number of stars, and we wonder, like this is what we've been wondering since humanity has started thinking about stuff, and like started wondering about the way the nature works, started thinking about what are the laws of nature. When we looked at the star, we started wondering, like, is there anybody out there, or are we alone in the universe? That's a very kind of a profound question that humanity has asked, and so far we don't have an answer for it. We can break this question into various parts and try to answer them with the different parts, and then maybe we'll be able to solve it. Like the first question that we could try and ask is this: is Earth, is the Earth something that is pretty unique? Is Earth the only planet which is unique in its nature? Is that the fact? So far, from what we have learned from past couple of decades, with this whole range of abundance of exoplanets that have been discovered, that is not the case. We right now know something around 5,000 exoplanets, more than 5,000, I believe. Many of them are Earth-size, and many of them are inside what we call the habitable zone. Habitable zone are these particular regions where we expect liquid water to exist, and so we believe that for the kind of life that has started on Earth, liquid water is one of the major component, and that is why we kind of try and find these kind of planets. But so we have found many of them. So it almost kind of suggests to us that Earth is no longer a unique place. There are other places in the universe which are equal and similar to Earth. So we ask this thing that when we look at the night sky, it's now already been kind of, we can say with some certainty that almost every star you see in the sky is likely to have some planets around it. Many of them will have Earth-like planet also. So planets are not unique. They are everywhere. Earth-like planets are also not unique. But what about life? Now that is where the question becomes a little bit complicated, because we don't have any other examples of life in anywhere else. The only examples we have is on Earth. So the question of like whether life can exist on extreme conditions is still not yet fully been answered. Astrobiology is a field which tries to kind of answer this question, like studying the origin of life, or like how life can survive in extreme conditions. We already have some examples of these extremophiles, which are these life forms which exist in extreme conditions, places where no one expects life to exist. Like, for example, at the deep bottom of the ocean, where there are no sunlights, but there's still life there. Even there is life in space. You might have heard about water bears. So life can survive and exist in extreme conditions. So these are all kind of suggesting us in the favor that probably life is not that unique on Earth. Life may be widespread. The other major evidence what we have seen on Earth is that even if the life once started, even if there are extinction events, life still finds a way. For example, what I'm showing you in this on this kind of schematic diagram is the entire history of life on Earth, starting from the very early single cellular life to the modern day most complex life that we have ever kind of developed on this planet. Throughout the history of these 4.5 billion years of life on Earth, there have been 6 major mass extinction events where almost all life got wiped out. But as a very famous quote, life finds a way. So once you have life, it is no longer going to be, you cannot really destroy it. It finds a way to survive. It finds a way to kind of develop. So which means that once you have life on any other this planet, once you get started with life, it may survive. It may evolve to this more advanced stage that we have on Earth. Now the question comes, with all these evidence, with all the sort of exoplanets we have discovered, with whatever we know about life on Earth, we ask this question. That means that there must be other life out there. There must be some other exoplanets which must be having some life on it. How do we go and find them? One of the ways by which people try to find them is this, what we call biosignature. I'll kind of leave all this discussion to Sujan's talk, which is going to happen tomorrow. So I'll suggest to folks to join in for that, where he will be discussing more on these details. But I just want to briefly mention some of the technique that people are trying to use in order to detect how the evidence of life. So for example, when a planet passes in front of the star, you can basically observe the transmission spectra of their atmosphere, or absorption spectra of their atmosphere. And you can basically measure what are the different elements are present in the atmosphere of these exoplanets. And if there is life, there are certain elements that you would expect to find. Like if there's a life like Earth, you might expect to find ozone, for example. So we try and find these kind of absorption spectra, but it is pretty hard. So far, it has been limited to only few. It's not been possible at all. With the recent sort of launch of JWST, when it will start its operation, we may be able to do this for a handful number of exoplanets, but it still will be very limited. We will not be able to do this for a large number of targets, because this is a very hard thing to do. The signal that we expect to find is extremely weak, so you can't really do this for large number of targets. So now the question is that how do we answer this question? Are we really alone in the universe? If life, for example, has started and it has evolved, it must have evolved to more advanced intelligence stage. That's our current hypothesis. Now, how do we test that hypothesis? There are various ways by which you can test it. There is a very famous couple of examples. People speculate that any life which becomes so advanced, they may run out of energy resources on their own planet, and then they look at their own parent star for excess energy. In some cases, people have kind of suggested that it is possible to build some kind of an enclosure to capture all the light that has been emitted or all the energy that has been emitted by its parent star. This was proposed by Friedman Dyson. That's why it's called Dyson sphere. But there are telltale signature of these Dyson sphere that you can observe them in infrared, although they don't emit light because all the light has been obscured by these artificial structure that been built by advanced civilization. But you can still basically observe the infrared radiation. So people have been searching for them. There are also cases where people have tried and found some examples of maybe possible Dyson sphere, but ultimately it was ruled out. One of the examples is the Voyager or Tabi star. I'll not go too much into the details about it. There are other ways to find intelligent life is to actually look at the physical evidence. For example, like we have launched these Voyager spacecraft, Pioneer spacecraft, which are actually now traveling in interstellar space. They are traveling at something around 17 kilometers per second. They travel, and there is no limit when they will to how far they could reach. But even with these velocities, they are not going to reach to any of the nearby star in any time in the future. Even it is going to take millions and millions of years, it may still never reach any of the nearby star. But it is one of the ways by which we have already kind of advertised ourselves to the universe. Like even if Earth get destroyed tomorrow, these probes will keep on traveling into the space, and if there are advanced civilizations out there, they may be able to get it or capture it, and then they would know that we exist out there. Similarly, we can hope that there are other probes out there which might be traveling through our solar system, and one would kind of like to find them. But again, this is a pretty tough problem. We may not ever find it because the range or the limit by which this thing can travel is pretty limited. So then what are the other ways by which we can basically search for the evidence of intelligence life? The best possible way we think is the electromagnetic waves. So electromagnetic waves are basically waves which can travel at speed of light. Basically, light itself is electromagnetic waves. What we see is as a light is a very, very small fraction of the electromagnetic spectrum. Electromagnetic spectrum actually spans a pretty large range, which covers the gamma rays. You might have heard about X-rays. If you heard about X-rays of kind of see if there are any fractures in the bone that you might have seen, ultraviolet, infrared, microwave that you might have heard, all the radio equipment that you use, like the mobile phone, Bluetooth, anything that you use, they all have radio waves to kind of communicate with each other. Satellites kind of communicate using radio waves. So these are various different ways. Ways electromagnetic spectrum can be divided. Now, on Earth, not all the electromagnetic waves from space can reach to the ground, and that is due to our own atmosphere. So our atmosphere is quite opaque to large fraction of the electromagnetic spectrum. Thankfully, we don't get huge amount of sort of gamma radiation from space because our atmosphere sort of absorbs it. So most of the large fraction, so what you're seeing in this plot, large fraction of more higher than light electromagnetic waves, frequency which have higher frequencies than light, typically gets absorbed by our atmosphere. And then also the middle part, the infrared part or the extreme high microwave frequency also gets absorbed in the atmosphere. There are only two windows, you can call it. These are the windows through which electromagnetic waves can penetrate the atmosphere and reach the ground. These two windows, one is the light. That's why we could see the universe. That's why we build telescopes through which we can see the stars, we could see the sun, we could see the moon. All this because the light from that can pass through our atmosphere and reach us. The second window of electromagnetic spectrum that our atmosphere allows is radio waves. So radio waves can pass through our atmosphere without being absorbed, and they could penetrate very easily. So they could reach ground and we could observe it. And that has given rise to this whole field of astronomy called radio astronomy. It's been there for like almost like 100 years now. where people have built what we call radio telescopes. So you might have heard or seen a telescope like this. But there are also telescopes. You might have seen this kind of dishes on top of different, and I mean, people have used now dish TVs. So you might have seen the dish antennas are there. Radio antennas are exactly similar to dish antennas. You might have seen, just much bigger in size. The concept is very straightforward. Like when radio waves falls onto the surface of the dish, they get reflected back, and then they get reflected back into what we call the receiver, where we actually capture these radio waves and convert these radio waves into electrical signals, and that we record with our digital instrument, and then we can play it back in our computers in trying to see what exactly we have actually captured with radio waves. So the idea is to basically study the universe in radio waves. This is what the radio astronomy has been doing. Now you can ask this question, like from ground, can we find a better way of like looking at the intelligent life? And the answer is yes. So our atmosphere is not the only factor. The universe itself, it seems tuned to favor radio waves. For example, our own galaxy, if you transmit a powerful radio signal from Earth, it can travel all the way across the galaxy and reach the other part of the galaxy, which may not be particularly true for other electromagnetic waves. Like you could transmit a high emission light, but then there are other sources of light which might not allow you to basically see that light for further out distances. So out of all the different electromagnetic waves, radio waves, coincidentally, is also one of the best ways by which we can communicate across large interstellar distances. So that's why we actually use this hypothesis and turn this argument around that, okay, if we transmit a radio waves, that radio waves can be detected across all the way to the other end of the galaxy, which means that if there is a radio transmitter out there, we should also be able to receive that. So that's where we kind of ask this question. So what we are doing in radio astronomy or in SETI is searching for these, what we call deliberate beacons, a deliberate radio signal being broadcasted by alien civilizations. And we can use powerful dish antennas that we have built on Earth to receive them. This is an example of a radio telescope. Unfortunately, that telescope is Arecibo, which last year has collapsed, so it's no longer in operation. But we have other radio telescopes which are also doing the same purpose. But why am I showing you Arecibo as an example is that if I transmit a signal from Arecibo dish, you can detect it all the way across the galaxy. So if aliens have built a similar kind of dish antennas, you may be able to receive the signal from them as well. Then there are also other classes of signal, which we call eavesdropping. So we use radio for our own communication purposes. We use radio for like detecting missiles. We use radio waves to detect asteroids in our solar system because we want to protect our planet. And in order to do that, we transmit powerful radio waves, which we hope to get reflected back from any kind of asteroids. And these radio waves don't really just kind of stop there. They keep on traveling in space. Now, these radio waves are so strong that you can still detect it from other end of the galaxy. So these powerful radar signals that we broadcast, these are not broadcasts that meant to try to kind of for any kind of alien's purpose, but we are using it for our own benefit. Now, but that radio waves, if on the other hand, is been picked up by an alien civilization, they would know that this is an artificial signal. This is not generated by any kind of natural processes, and they would know we exist here. Similarly, we can also ask this question, like if aliens are using radio waves for their own benefit, for their own communication, they may be communicating with their own satellite, they may be communicating with their own space probes, they may be using radio waves to detect asteroids in their own solar system. Those radio waves don't really stop there, they reach us. And that's how we could detect it. Now, you can ask this question, like what are the likelihood of finding such a signal? What is the likelihood of really any kind of alien civilization to be out there? That's a pretty hard question to ask. You can actually look at a probability of that. Like what is a fraction of stars which will have a planet on it? This is what we call the Drake equation. And I will again refer you to Sujan's talk on this slide. But what I want to kind of show you is that it is a probability game. We don't know exactly how many civilizations out there which are broadcasting because it's actually multiplication of various factors. And there are so many unknowns out there. Like we know that how many stars have planets around it, but we don't know like how many of those planets will have life on it. We don't know how many of the life might have evolved to become intelligent. How many of them might be transmitting radio waves. So these are some unknown factors that we don't know. So we just can basically probably take a guess on it. So you can take optimistic or pessimistic guess. So if you take a very optimistic guess, there is a likelihood that we might have one intelligent life per million stars. So every million star will have at least one intelligent life, which is broadcasting radio waves. You can be pretty pessimistic about it, and then the life will be pretty rare. It may be that only one, you might find one intelligent life in 100 galaxies. So that's pretty rare case. But overall, this is what I really want to kind of focus on. We don't know. We have absolutely no idea what is abundance of intelligent life out there. So the only way, I again like to kind of quote Carl Sagan in this, that the only significant test of the existence of extraterrestrial intelligence is an experimental one. So unless and until you do an experiment, you do observation, and you test it, there is no way for us to know whether our optimistic or pessimistic scenarios are true. And that's exactly what we are doing. So Breakthrough Listen program or Breakthrough Initiative was launched in 2015 with the sole purpose of searching for extraterrestrial intelligence. It was launched at the Royal Society London, and we have several dignitaries who basically signed and who were on our advisory board. You might have all recognized Professor Hawking over there, and also Professor Martin Rees. And you can see our generous donor sponsor, Yuri Milner, who basically gave us the funding for this program. Our goal for Breakthrough Listen is a part of Breakthrough Initiative, is to search 1 million nearby star. So if you assume a very optimistic scenario, as I said, you may find life in 1 star per 1 million star. So that means that if you search 1 million star, you may be able to find another life out there. If you take a very pessimistic scenario, you might find one intelligent life per 100 galaxies. So we are also searching not just nearby million star, but we are also searching nearby galaxies as well. We are also looking at our entire galactic plane. So this program is basically committed to run for 10 years, and we have a funding for, I think, around $100 million. The amount of data we collect in a single day of operation with Breakthrough Listen is equivalent of every previous year before Breakthrough Listen search that people were doing. So this is definitely a huge leap forward in terms of what people have been doing in terms of searching for this signal. Now, the idea that I mentioned is not that new. People have thought about it since last 60 years or so. People have been trying to search for these kind of signals for past 60 years, but they have not been successful. The reason is that there is very little that search has happened. There is very little parameter that they have explored. But with Breakthrough Listen, we're trying to expand that. So again, I try to reiterate the exact idea of Breakthrough Listen. What are we trying to do? So let's assume that this is our galaxy. Our galaxy has many stars on it. Let's assume that these stars, some of them have intelligent life on it, and they are broadcasting these radio signals. Now, these radio signals are kind of like bubbles. These are, you can assume it as a 3D bubble, which are expanding in space, and they travel throughout it. Now, let's zoom in on a planet. This is like an alien planet. Let's assume this is an alien planet which has life on it. Now, over the time, life became intelligent. That life developed technology and then started broadcasting radio waves. That's how the radio waves, even they are deliberately transmitted, or we just kind of using them for our own technologies, keep on transmitting. Now, for some reason, that somehow stopped. So you see this bubble, even if they are not existing right now, there are these radio bubbles which are always there when they're ever kind of crossing the Earth. So sometime it may happen that one of these radio bubbles reaches the Earth, and then you start seeing the radio signal coming from one of these civilizations. So what you can do, you can use a radio telescope like this, and when it receives the radio waves, as I mentioned earlier, we already have them attached to computers, and which can record the radio waves, and through which we can detect it. That if there are actually radio waves coming from anywhere in the sky. And that's how we use whole number of radio telescopes. So we are not just doing this for a very small number of telescopes. We are doing this for whole range of telescopes where we are trying to kind of enable SETI activity. So this is kind of part of my job. So we have some observatories which we call our primary facilities for Breakthrough Listen, which includes the Green Bank Telescope, which is in West Virginia, and Parkes Telescope, which is in Australia. So these two telescopes, we have a couple of other primary observing facilities as well. We also observe in optical, but I focus mostly on radio. So these telescopes are our primary observing facilities. And these facilities actually work with us for 20% of their telescope time for doing dedicated SETI experiment. Then there are a whole number of other radio observatories which spread throughout the globe. Some of them are in Europe. Some of them are in China, like the FAST telescope, which is currently the world's biggest radio telescope. It's actually a 500 meter in diameter. So just think about it. This huge, massive 500 meter dish sitting on the ground. This is a massive radio telescope. We also have telescopes in India, like the GMRT. I'll speak about it in a minute or so. Then we also have telescopes in Italy, in France. So we have radio telescopes which are spread all across the globe, which are purposefully doing experiment to search for these kind of signal. Just to give you an idea of the sheer size, so this is the Green Bank telescope. It's 100 meter in diameter, so it's massive, massive dish. You can see the size of humans standing on it. It's actually the size of a 2 football field. So it's a super enormous size, and you can see that you can see, maybe if you can zoom in, you can see a tiny car parked right next to it. So this is a massive dish, and it's looking for these kind of signals. Why do we need these kind of these big dishes? Because the kind of signal we're trying to detect are extremely weak. They are not pretty strong. So you need big dishes in order to basically detect them. But there are a large number of challenges that we have. So when a radio telescope is looking at space, looking for these kind of signal, they are not really only detecting stuff from space. Radio telescopes are pretty powerful. They can also pick out signal which are generated by our own technology. This is what we call radio frequency interference. For example, if there is a car passing by, cars have radio transmitter on it that can produce radio waves. Stars have GPS, which might be communicating with satellites, and then you can have radio transmission coming from satellites as well. You might have transmissions coming from nearby transmitter tower, any kind of aircraft that is passing nearby, Wi-Fi or Bluetooth that we use. All of that actually contributes the radio waves to basically they sips in to our signal analysis chain, and they really disrupt, and they are the major problem in order for us to search for this intelligent signal, because this is the kind of signal which kind of mimics the type of signal we are searching for it. So it's one of the biggest challenge for SETI in order to, how do we identify these signals? How do we separate them? So radio frequency interference is a major challenge. So we use some very peculiar observational techniques in order to eliminate as much of radio frequency interference as possible. Now, one of the techniques is what we call positional switching. So when we use a bigger telescopes like GBT, we point it towards a star, we record it for some amount of time, and we see, let's say this is our target star. We hope that there is an alien or extraterrestrial intelligence are out there in that one particular star. So we observe that star for some amount of time, and then we observe a different part of the sky. They go back and forth 3 times. If the signal that we are interested in persists on towards only direction where we are pointing toward the star, that is a good indication that it's actually coming from the star. The reason is that the typical interference from our surrounding does not have directionality. So no matter where you look in the sky, they always come in. So this is a way by you can distinguish if something is truly coming from the sky or not. The other way is by people, what they use this called multi-beam approach. So if you have multiple beams in the sky, so Parkes radio telescope earlier had these 13 beam receiver. So it was simultaneously looking at 13 different parts of the sky. And let's assume that one of the beam is pointed towards our star. So let's say this is our target star and our beam is pointed towards that. So if you detect a signal only in this beam and none of the other beam, that is again an indication that the signal is actually coming from the star, not anywhere local, because the local signal will probably be picked up by all of the beams. Similarly, you can form, these are what we call digital beams. So you can use interferometers. I'll not have time to go into the much details, but you can form multiple beams in the sky where you can look at different targets and you can basically do the same thing. So with that idea, we can basically eliminate as much of interference as possible. Now, GMRT, why that GMRT is important for experiment like this, because I think most of our audience is from India, and we should feel proud about this instrument we have. The GMRT is actually one of the best sensitive radio telescope in the world at lower radio frequency. There is no other radio telescope in the world which come anywhere closer to the sensitivity GMRT has. The bigger advantage GMRT offers is that the antennas of GMRTs are spread across 25 kilometers. So if you detect a signal, we can basically cross-correlate signal from all of these different antennas. So unless and until the signal is skybound, so like all of these antennas are looking at the same source. So if the signal is coming from the source, they will be present in all the antennas. But let's assume that there is some interference local to some antennas. That signal might not be present in the other antenna. Let's say you have some transmitter closer in this part, the signal will be pretty weak or may not even be picked up by antennas which are this far apart. So you can use these long distances between antennas to distinguish what is basically local and what is coming from the sky. So in fact, I just want to advertise this. So we had a summer junior research fellow program, which we will be announcing very soon. We already had a program going on with the Amity University, which has a pretty good astrobiology program. And we are currently having a 4 junior research fellow working with us. In future, we will be also continuing this effort to hire more junior research fellows. So if any of the members in the audience are interested to work with us, please be on the lookout on the Amity University channel, where you can basically work on a SETI project. Okay, so GMRT is great. So it has this 25-kilometer distance between antennas, which can easily separate out what is local and what is skybound. We can do something even better. So we are currently trying we have already done it. We are using these 2 antennas, with our 2 low-fast stations in Europe. So one station is located in Ireland, and another station located is in Sweden. So the total distance between these 2 antennas is something around 1,300 kilometers. That is far apart. That's pretty far. So both of these antennas are actually observing the same target. So if you have some kind of a local transmitter, which is local to one of the antennas, it may not be picked up by the other antenna. So this is a way by which we can distinguish what is actually coming from the sky and what is basically coming locally. Now, this is a pretty challenging problem. Like we need a huge amount of computing resources to basically record all of these signal that we receive. So we have built one of the world-class instrument to basically record signal from antennas. As I mentioned earlier, when radio waves falls onto the dish, they get converted into electrical signal. Now, these electrical signal gets recorded into this massive cluster of computers. And I can just give you an example of our biggest compute cluster we have. This is at the Green Bank telescope, which can record something up to 12 gigahertz of bandwidth. But most importantly, it can record at 190 Gbps. So it can record 5 DVDs in 1 second. It has a storage capacity of something around 250,000 DVDs. So it can basically keep storage of 250,000 DVDs in it. So it is massive computer which can record all of these data. Now we may ask this question: what do we do with all this signal that we collect? What are the kind of thing we kind of search for? So one of the very classical signal that we all search in SETI is called narrowband signal. This is just one of the examples. I'll come to another example, other ways by which we can search for ETIs, but this is just one of the examples. So any kind of signal, what you're seeing in this plot. So let's say this is the voltages, or this is the kind of signal that you receive from an antenna. When you take a Fourier transform of it, typically every signal consists of various different radio frequencies. It is not just one frequency. It consists of many, many radio frequencies. Almost all astrophysical sources have broadband signal. They consist of many number of frequency channels. So when you take a Fourier transform, you see multiple frequency lines. So we can break this signal into multiple frequency channels, multiple frequency. So you can basically divide the same signal into multiple frequencies. So any astrophysical signal will have multiple frequencies which are all combined together, and that's what you are seeing. But an artificial signal will be very unique. It will not have multiple signals. It will not be broadband. It will be very much narrowband. So this is an example of narrowband signal where the x-axis is again the frequency, And y-axis is kind of like a time on the top plot, and here it's just kind of showing the intensity. You can see that this is an example of a narrowband signal because the signal is only present in a very, very small frequency channel. It is not present anywhere else. This is a very clear-cut indication of signal being artificial because none of the known astrophysical phenomena have produced or have seen to be producing narrowband signal. There is no theory which can kind of suggest that signal from astrophysical sources will be extremely narrowband. So we are searching for signal which is only like 1 hertz wide. Typically, signals like this do not exist in nature. So if you detect a signal like that, that is a very good indication that it is actually coming or being produced by artificial processes by extraterrestrial intelligence. That's not just the one class of signal. We also search for other classes of signal. We search for different kinds of modulation. We also search for broadband signal which kind of sweeps in time, which has various different shapes and sizes across a large range of frequency. Again, we take our sort of lessons from what nature produced, and we ask this question: what are the ways that nature can never produce these kind of broadband signal? And then we kind of go ahead and search for them. So there are also classes of broadband signal which nature does not produce. So we go and search for those kind of signal. You may ask this question: what have we sort of found so far? So I'll suggest you to our very recent published Nature Astronomy papers, in which we advertise a discovery of a very peculiar signal, which we named as Breakthrough Listen Candidate 1. Although later we ruled out that the signal had all the characteristics of being artificial and extraterrestrial, it was still most likely interference. But we came very close. So this was a very good exercise for us to know how do we basically separate out signal which are still artificial, produced by our own technology, but might mimic being artificial or being extraterrestrial. There are many challenges for this kind of task. For example, what I'm showing you in this plot, it may be pretty hard to see, but you will see time kind of speeding up. And we are looking at a star over here. Let me kind of roll it back again. So what we are seeing, what we are targeting here, we are observing a star. And I mentioned this earlier. The way we do is that we observe the star for 5 minutes. And for 5 minutes, we look in a different part of the sky. So that is our target star. What you see rest, these are all satellites. Now, satellites populate the sky quite a lot. And that is a problem because sometimes these satellites pass right where we are looking and they can produce the kind of signal that we are searching for. So this is a major challenge for us. So I would suggest you to kind of just focus on this part. So this is a target star we are observing. We observe it for 5 minutes and then we look off. There is empty part. We look on. And then when we look off, it happened to be that at the time when there was a satellite which was passing in the off position as well. So, I mean, that's just an example, but this is the problem that we have to tackle. Like these satellites kind of pass throughout the sky. There are some of these are low Earth orbit satellites, so they move pretty quickly. Some of them are geostationary satellites, which are focused and kind of located in one part of the sky. But especially these satellites, when they come and go, they introduce a lot of interference, and they are the big challenge for us. So how do we deal with it? Even if we have these kind of signals to search, what do we do? So that's where machine learning or artificial intelligence comes to our rescue. We've been very successful in order to develop various different machine learning algorithms in order to isolate these kind of signals. So there are two ways in which you can use machine learning. You can use machine learning to find known types of signals. So that is what a large domain of machine sort of image identification that's been happening. And one of that image identification is called convolution neural network. This is quite popular. You might have heard about it. Many of you who have actually even taken a basic course on machine learning, the first thing you might have learned is convolution neural network. So convolution neural network is just by training a neural network to identify kind of stuff that you are searching. So you can basically train with a large number of set of examples. You can say, okay, these are different pictures of cat. These are different pictures of dog. And if you give a different picture to the neural network, it can easily identify whether that is a cat or a dog. And that's been heavily used, for example, in self-driving cars, but people are currently trying to kind of facilitate and enable. These are using convolution neural network techniques. So you can use convolution neural network technique to search for kind of signal that we already know that might be an indication of artificial intelligence or artificiality being generated by extraterrestrial intelligence. I gave you an example of narrowband signal. So we can train a classifier to search for narrowband signal. You can train a classifier to search for different kind of modulation, different kind of sort of broadband signal. So that's one classes of signal that we can certainly do, and which we are already doing. We have a couple of papers on it out there already, which actually searches for these known classes of signal using machine learning tools. Then there is another class, which is called unknown or anomalies, signal which we can never really envision. Like obviously, this may be the most interesting class to search for when we are searching for ETIs. The reason being that all of these signals that we have basically thought about, they may still be very much anthropocentric. Like they may all be just the way we think about how to communicate. There is no way that ET is bound by these limitations. And advanced extraterrestrial intelligence might completely think about something that we have never really thought about, might really think about a signal that we can never really kind of train a machine to identify. And for that, we use anomaly identifier. Even then, we can use machine learning. The reason is that there are ways by which you can train a classifier to identify patterns in your signal. This is heavily being used in speech recognition. So when you sometime in YouTube, when you see a caption, so many times these captions are actually enabled by these technique called long short-term memory networks. So you can feed entire language and you can ask this question to a neural network, like what is the expected outcome, or what is the expected next observation? And then based on its previous observation, it can make a prediction. Okay, if it has seen this before, then it is expected to see this next. But in case of anomaly, if there is a strange signal, which we have never really seen before, if we ask this, then it doesn't fit the prediction. So what we could do, we can take all the radio data that we have gathered over the years, and then we can feed that into this LSTM, and we can make predictions. So we can use this already kind of gathered data, which we already know that they don't really have any evidence of extraterrestrial. And then that it can train a classifier, which can identify things which it has not seen before. So if you point your radio telescope towards an interesting target, you see something unusual which you have not seen before, that would be a very good indication that that's something interesting to look. So you can use these classifier to identify unknown classes of signal that we have really never thought about. We never really think that they exist out there. So that's another class of signal where artificial intelligence is helping us identify the signal. But combining with all that, unfortunately, I have to kind of say this, that we have not found ET so far. Although we've been searching for last 5-6 years, we don't have very good, strong evidence of any kind of signal that we can say for certainty that it has been produced by intelligent life. But that is not to be kind of feel down about, because the reason is that we have just scratched the surface. We have not really searched our own galaxy at all. If you zoom into the region, so let's say this is our spiral galaxy, and we are located somewhere here. And if I zoom this square region, the green part is the region that we have searched. So we have only searched our nearby star. There is a whole number of stars that's out there which we have not yet even searched. So maybe ET is out there. Maybe the argument is that maybe it's somewhere between the pessimistic and optimistic. Maybe there is intelligent like 1 in 10 million star, maybe 1 in 100 million star. We have not really ruled that out. We don't know that. So unless and until we do the search for all the stars, to large number of stars for large amount of time, we cannot really rule it out that ET do not yet exist. And that's a massive effort. So in a way, as I said, that we just started. We haven't really done that much. It's just like saying that if you fill a glass of water from the ocean and you say that, okay, there are no fish in the ocean. It's just like that. We have, if the amount of sort of parameters that are required to really do the search, if you take all of this parameter and the parameter that we have searched, it's equivalent to a glass of water, and the amount of parameters out there is equivalent to an entire ocean. So we have just begun to do this search. And you can contribute. So if there are any students out there and they would like to help us, all our software that we have developed to search for the signals are open source. All the data we collect, this is one of the bigger thing about Breakthrough Listen, that Breakthrough Listen makes all their data public. We don't really have a proprietary period that we hide the data from the public for a certain amount of time. As long as it is possible for us to make it public, we make it public. So in some cases, we have made it public even the next day, because there are some interesting target that we observed, and it's probably interest of the community. So we make all public. So we have a software which is public. We have data you public. You just need to go to our website and get the data, get the software, and do the search on your own. In fact, a couple of students have already done it. So there is, in fact, a high school student, David Lipman, who actually led a paper on searching for laser lines. He did it for optical data set. But again, same idea. All the software that he did use was public. All the data that was there was also public. He just downloaded it and he used it. So it's open to anybody in the audience. If any of you are interested in working on it, please reach out to me, or you can just go to our website and you will find all this detail. All right. So this is a nice my last slide. So are we alone in the universe? We don't know. I mean, we are currently in the new era of to answer this question. So far, we have not been successful, but maybe we have not really searched that far. So to kind of sum it up, if you look at the number of exoplanets out there, it's most likely that Earth is not unique. Planets are not unique. They are everywhere. Life is probably not unique either. Maybe life is pretty common. But the intelligent life may be tricky. Maybe intelligent life might be rare. And in order to really answer whether it's rare or it's widespread, you need to do an experiment. You need to basically do these observations and basically validate this hypothesis. And that is what we are doing. We are using radio telescope. We are using artificial intelligence in order to basically answer this question. So stay tuned. Hopefully we will find something very soon. Thank you very much.
Thanks a lot, Vishal. That was a fantastic talk on a topic which is not just of scientific interest, but also of popular interest among everybody. There have been none of us who have, very few of us have not thought about alien life or visiting aliens or UFOs when we were children. And it's really nice to know that we now are having substantially well-defined experiments to try and detect signals from other life in our galaxy and elsewhere. So we will now get questions from people. If you have any questions, please just type them out in the Zoom chat or the YouTube chat, and I'll read them aloud. So Vishal, shall we start with the questions? The first question is from Rameshwaran. How do radio waves pass through the atmosphere but not other electromagnetic waves? Is it due to their frequency?
Yeah, so some of the electromagnetic waves have high energies. So special water molecules in our atmosphere typically absorbs them. So that's why they don't really typically pass through our atmosphere. And it also to do with what different molecules we have in our atmosphere, which basically absorbs. So anything that has certain energy can easily get absorbed by molecules. So if certain things do not have sufficient energy, then they don't get absorbed. So fortunately for us, radio waves don't really carry that much amount of energy. So they don't really get absorbed that often, and they get easily passed through. While some of the high energy electromagnetic waves have extremely high energy. So you get absorbed by molecules in our atmosphere. Also, many of these high energy, so in order to detect them, I mean, we still do astronomy with them. We do have gamma ray telescope. We do have X-ray telescope. In fact, India has one of the best sort of AstroSat telescope, which is currently operational, but it is located in space. So you need to go outside our atmosphere to detect them and study the universe. So people do study them. People do basically understand various aspects of the universe at these frequencies, but you cannot do them from ground. You have to go to space.
Yeah, thanks, Vishal. The next question is, what are India's projects this decade in astronomy? I will postpone that question to later, and maybe we can take that at the end. How exactly do radio telescopes help in astronomy other than ET detection and radio wave spectrum of other stars?
Well, radio astronomy is a kind of wide field. I mean, there are a huge number of things radio astronomy is kind of able to contribute. I can just give you like one or two examples. Like radio waves or radio astronomy was the first way by which we came to know that we live inside a spiral galaxy. Like radio waves are pretty powerful way to kind of detect stuff at farther out distances, as I said, like infrared and optical wave get absorbed, like because, for example, dust in our galaxy absorb light. So you don't see stars which are so far away. But for example, if there is a gas cloud, typically hydrogen emits pretty bright radio waves. So if you have a hydrogen cloud far away, signals from it kind of reaches to us. So people basically map the way how hydrogen is spread in the sky, and they could map that, okay, there are gaps in these hydrogen cloud, and that's how we came to know that we live inside a spiral galaxy. Think about this, like, how do we ever know? We cannot go above the galaxy and see the galaxy from the top to see, okay, we are living inside a spiral galaxy. So radio wave was the only way by which we came to know that we live inside a spiral galaxy. Not just that, radio wave has kind of helped us understand a huge number of phenomena in the universe. For example, this very particular high energetic phenomena called pulsars were discovered in radio. Pulsars are high energetic neutron stars, which have these wide radio beams. And they were first discovered in radio, although now we detect pulsars at other wavelengths as well. But pulsars were pretty high, interesting objects. Still, we don't know a lot about pulsar, like what are the emission physics? How do they produce these radio waves? And there is a huge amount of sort of field in order to understand pulsars. But we came to know them through radio waves. We studied the radio waves from galaxies which are so far away, you can't even see them. But the radio waves coming from them are so bright. There are these we call AGN and quasars, which have so bright radio waves that you could detect them even if they are billions of light years away. So you can basically study the entire universe, not just things inside of our galaxy using radio waves. So radio waves is a whole range of things that people can do. And SETI is a very small subset of these things. So SETI is not just the only thing radio waves help us do. These whole new things that astronomy can basically do with radio waves. SETI is kind of part of it. I guess the second question is, what are the India's bigger projects for radio astronomy, or just in general?
For astronomy in general, so we can take that at the end.
Yeah, sure. I mean, I maybe there are other people who are more qualified to answer the question than I.
I'll call on others for this. Thanks, Vishal. So let's go to a couple of questions from YouTube and come back to Zoom. The couple of questions from Aniket Prasad. The first is existence of liquid water enough to classify planets as potentially habitable, or is there a kind of model which also considers other parameters like biological, etc., to mark a planet with intelligence? And his other question is, can you explain how do we differentiate between SETI signals and artificial RFI signals?
Yeah, so I'll I'll get the first question. I mean, again, I refer you to Sujan's talk. Professor Sujan is going to give a talk this tomorrow on this question of how do we detect biosignature. To answer this question, whether water is the main ingredient for the origin of life, we don't know. We have only one example of life that we know on Earth. And so far what we have learned is that water is is a good solvent, and it is pretty necessary for many of the chemical processes that are necessary for basic building block of life, basic sort of origin of life. So we hypothesize that water is pretty kind of necessary in order to have kind of life that we have on Earth. Now, that may be just our limited example. Maybe there is a life out there which doesn't necessarily need water. They may use some other chemical as solvent to do all the different chemical processes. We don't know that. We have not really come across any other technique or tool in our laboratory that can help us with that. So far we have only good example is water. I'm not an expert on that, but that's what I kind of tell you, and that's why we kind of go ahead and search for them. And the second question is, I guess, how do we differentiate between the signal which is truly coming from ETI versus that's been generated by our own technology? So that's how I kind of give these examples of various different observation technique. You look at different parts of the sky. Typical signals that are generated by our own technology are not going to be bound to one part of the sky. They will be coming nowhere where you look. So that's the one way you can distinguish it. The other way is using machine learning tools. So you can classify known kind of signal using machine learning tools, things that you already see almost on a daily basis. So you can train a classifier to classify these kind of signals which you already have seen before. And that could be one of the ways by which you can distinguish it. So there are a couple of ways by which you can distinguish things which are truly coming from the sky versus what is being generated by local technologies.
Thanks, Vishal. And radio interference from man-made technologies is becoming a huge problem for all radio telescopes in the world, including India. There's a question by Manish Sanghani on YouTube. Wouldn't it be an advantage to put a radio telescope in space in order to eliminate radio frequency interference from Earth-based instruments?
Sure. There is already a radio telescope in space called Radio Astron. But as you would know, getting anything into space is hugely expensive. I have one slide on that. So anything you want to bring to space requires a huge amount of money. Even if you want to bring like a kilogram object into space is a huge money. So building a radio telescope in space is massively sort of a huge endeavor. So I don't think so there is a huge amount of funding resources available to build massive radio telescope. In fact, this is kind of like a hypothesis or a white paper we propose that building a telescope, or for example, on the far side of the moon would be an ideal way to shield all the interference of Earth, because as you know, moon is always facing one of its side to Earth, while the other side, which we call the dark side of the moon, is always away from Earth. So basically, if you build a radio telescope on the other side of the moon, it can get shielded by all the interference being generated by Earth. So that will be a massively a great way to eliminate our interference. But bringing anything to the moon or even space is heavy, massively sort of expensive. So we have not really kind of reached that level yet. But hopefully in future, we'll have funding resources to do that.
Thanks. One last question from YouTube before we come back to Zoom. And I invite other people on YouTube and Zoom to post your questions, but also with the caveat that please post your questions about the topic which Vishal talked about. We will not be taking questions on other topics which is not covered in this talk. There's a nice, interesting question from Rajpal Singh. Does a living being emit radio waves?
Living being, I don't think so, emit radio waves. It requires, I mean, we have tried and detect like brain waves in the sense like there is anywhere. So what is radio waves? Basically, it's electromagnetic waves. Anytime an electric basically current passes through any medium or anywhere that the electron basically either changes its path, it produces electromagnetic waves. So there are ways by which you can produce them through human or like living organism, but it is extremely tiny. It is not really producing in a way that we can detect it. Typically, most of the electronics that we see are our major problem. So it is not the human or the living organism that is the problem. It's the technology that is what we use is the problem.
Thanks. Coming back to Zoom, and I think people who type the questions can just unmute themselves and put their videos on and ask it. I'll call on you one by one. The first is Zagar Narasimha. Would you like to unmute and ask your question?
Also,
yeah, please go ahead.
am I audible now?
Yes, I can hear you.
Yeah, like, is there any other ways other than using electromagnetic waves to detect ET?
Yeah, so Breakthrough Listen is actually looking at not just radio wave. I mean, I can give you an example of this one particular thing. We are also looking at optical domain. So as I mentioned earlier, I think we talked about this earlier, from ground-based instruments that are located on ground, we can only detect radio waves and we can only detect light. So you can either use radio antennas or you can use optical telescopes. So we are using both of this. So radio is not the only way by we trying to search for ET. In my today's talk, I only focus on radio, but we are also looking at optical light, like for example, extremely narrow band optical light, which we call laser emission. So typically all the astrophysical objects, they emit light, but they are not narrow band, they are broadband. So if you detect similar argument, if you detect extremely narrow light, which is what we call laser is something that we can artificially produce from Earth. If you detect some kind of a laser light signal, which is only focused on a very, very small part of the optical spectrum, that is again an indication that it is artificial. So yes, we do search at other domain, not just radio.
So like, can we even look out for neutrinos or else gravitational waves other than electromagnetic waves?
Sure.
Is there any possibility?
No, yes, of course. So people have been suggested and proposed this, but as you already know, detecting these things are extremely difficult. Like detecting neutrinos or detecting gravitational waves is extremely, extremely difficult. Moreover, the amount of energy that is required for like for ET to transmit gravitational wave is so enormous. Like they have to wobble a black hole with some kind of a non-random fashion or some kind of in a way that is indicator of artificiality. Now, the amount of energy required for that is just so enormous. You can build a radio transmitter with a fraction of the cost, which can still serve the same purpose, which can still send the signal across large distances without you spending that much amount of energy. So you also have to ask this question that, yes, there are other ways by which you can transmit yourself, but what is the most energy efficient way? What is the way by which you can do this with the best effective and least costly manner? And that is, again, radio waves.
Okay.
Sir, thank you, sir. So,
Thanks.
another thing is can you mention the website which you said where we can find the open data and software?
That's it.
So to interrupt, Vishal, what we'll do is, since a lot of questions about online tools and so on, we will collect the information from Vishal. We'll put them up on our website and social media later. Links to all the important tools and web pages which Vishal thinks you should have. So we'll do that on a later date. It will be on our social media. It will be on our website. Okay.
Yes.
Thank you, sir.
Yeah. Next, I invite Avani Dabke to ask the first two questions. The third is kind of out of scope for this talk.
Yes, hello, sir.
Yeah, please go ahead.
So my first question is that how do we convert EM waves into sound? And the second question is that if their light exists in the Milky Way, let's say, then what are the conditions that would be preferable, and what is the region where there is the highest probability to find another light?
Okay, so I'll come to the first question. How do we convert the radio waves to anything that we can basically hear by our eyes? So this is a kind of maybe a wrong impression. So when you talk about radio wave, people feel that radio astronomers are basically listening by the microphone, but by the speakers. No, we are not really doing that. You can convert anything to audio waves. It is not really, you can even convert optical to audio waves. You can just have to bring it down to lower frequencies. So anything like, for example, radio has some energy, right? And that energy is fluctuating. When a radio antenna is nothing but simple wire. When a radio wave falls onto this wire, electric current goes up and down these radio antennas, and that generates electric current, which you can record. So once you have a changing current, you can basically get it out and record it into a computer, and then you can plot it. If you want to hear it, that's what typically we do. We do radio astronomy by just making images or basically looking at the radio waves as how they change as a function of frequency and all that. We don't really listen to the radio waves, but if you really want to do it, you can do it. It is just that you have to down convert it to a lower frequency that is audible to human ears. You have to basically convert and tune it in a way which is in the frequency range that is audible to human ear, which is what I think up to 16 kilohertz. And then you can listen to it, but that's not what we do. To answer your second question, what are the regions as the things that we think that are most likely of in our galaxy the life to find? I think that's a pretty good question. This gives me an opportunity to talk about one of my other projects. So I'm also leading a project of surveying the center of our own Milky Way. Let's see if I have a slide for that. Yes. So this is our Milky Way, right? If you look at the center, a direction of that center has the largest number of stars compared to any other direction, because that's where the large number of stars are gathered. So if you look at towards the center of our own galaxy, that's where you are likely to encounter almost like billions of stars. So that is a large number of stars compared to any other direction in the sky. So that kind of just gives you an advantage of only pointing a telescope and doing a large survey of one part of the sky and also having a large number of targets in the same part. So galactic center, I would suggest, is the highest possible region where one can expect to find some evidence of life if it exists, for example. So we are doing the surveying the entire galactic region, entire galactic center region for that purpose. So I hope that kind of answers the question.
Yes, sir. Thank you.
Thanks. So I invite more questions both on YouTube and Zoom, but please remember we will entertain questions only if they're about this talk and related material, matter. What questions about black holes and so on, there are other talks where you can come and ask those questions. Vineet Lobo, would you like to unmute and ask your question, please?
Hello, sir. Hello.
Yes.
Yes, please go ahead.
James Webb telescope, we can send telescope to space, which is taking visible light and UV rays. So like that, can we send a radio telescope or antenna to space?
Okay. Well, I guess I already kind of answered that. Like, it is, yes, possible. In fact, we have radio telescope in space called Radio Astron, but bringing a telescope to space is very costly and expensive. So we don't necessarily have that much of funding resources to do it. But hopefully in future, if there is enough funding resources, we'll be able to launch telescopes in space. Yeah.
Thank you. Are there other questions about the talk? SETI, getting signals from intelligent life, how to use a radio telescope? Oh, there's one question which we can probably go back to. Yeah, let me get that. Rameshwaran, we didn't ask your second question about single dish versus multiple telescopes. Do you want to ask that question? Rameshwaran, you can unmute and just ask. Okay, let me then read out the question he has. What's the difference and advantage of a large dish radio telescope versus many small telescopes connected to each other?
Yeah,
in this context.
Yeah, sure. So I mean, it's a good question. Obviously, the whole game is about sensitivity and resolution. So how sensitive or how weak signal you can detect, and what is the smallest region of the space you can basically see in order to detect the signal. So there are two things that kind of goes in hand with each other. Large single dishes allows both of this. Large single dishes allows you to be sensitive to weaker signal, and due to their enormous size, they also allow you to see things which are extremely sort of coming from a very small part of the sky. This is what we call the radio beam. Lot of single dishes are obviously helpful, but you need to, if you want to kind of mimic what a single large dish do, you need that much amount of collecting area, then you need a lot of them. But the best advantage is that you can place them so far away from each other that can simulate a dish that you can never build physically. So you can never build a radio antenna which is 25 kilometers in size, because that's just physically not possible. But you can place antennas like GMRT did. You can place individual small dishes which are spread across 25 kilometers. Like this is a telescope called Meerkat telescope, which was in South Africa. And this is a telescope in India called GMRT. Both of them are using the same concept, that they have antennas which are spread across so large distances from each other, which mimics having a single dish, although with a much lower collecting area, but that gives you that kind of sort of resolution that you will be able to see the details of anything that's happening in the sky to that finer sort of sky location. That's very useful for doing SETI as well, because in SETI, we don't know whether the signal that we are receiving is actually coming from our own technology or whether that is coming from the sky. Single dishes, you have to use some different technique. Either you have to do like multiple beams, or you have to do what we call position switching. So I mentioned this, you have to look at different part of the sky in order to eliminate that. While array antennas or collection of large number of small antennas already allows you to do that. So you don't need to do this positional switching, because single dishes, you can cross correlate signal from multiple antennas. And only thing that is actually common to all of these antennas will come out brighter when you do this cross correlation. Things which are which are local to one antenna and not really present in the other antenna kind of goes down. So you can basically look at signal and see if the signal is persistently present across all the baselines or all the different antennas in a similar strength as expected strength. Then that is a way by which you can distinguish if it's actually coming from the sky or whether it's actually local. So it's very useful for a SETI to use multiple antennas rather than using single antennas.
Thanks. HS Harsha, would you like to ask your first question, which is about Hubble Space Telescope and UFOs? HS Harsha, you can unmute and ask your question. Okay, I think they're not here. They had logged out. So I will read out the question. They say that Hubble Space Telescope has detected some sort of moving UFO. Is it true?
I don't think so that I have seen any kind of things like that. No, I mean there was one incident called Oumuamua. There was an extrasolar asteroid that entered our solar system, which showed some indication that it has a very peculiar nature. Like first of all, it was pretty elongated. Typically, asteroids or comets are built which have pretty symmetric shape. This one particular object that was detected called Oumuamua had pretty unusual shape. And the second thing was that people noticed that, in fact, we detected it when it was leaving our solar system. They noticed that it was accelerating. Why would because anything that comes closer to the sun, due to the gravitational pull of the sun, it gets acceleration. But when it is leaving, it should decelerate. But it was happening the other way around. Like when it was leaving, it was accelerated, and people hypothesized that maybe it is an alien probe, which was just came to visit and then it was leaving. But there are also natural explanations for that. So people have suggested other ways by which you can have acceleration from these objects. So I don't think so there is any concrete evidence of anything related to that. So especially in terms of general, in terms of UFO, I'd like to just make a statement that we don't work on UFOs. SETI is not really looking for UFOs. We are not like looking at the sky and looking for these alien spacecraft. SETI or like Breakthrough Listen is a very genuine sort of scientific effort where we use scientific method and technique to look for things which we think are the ways by which we can eavesdrop on activities of extraterrestrial intelligence. If they are using radio waves or optical waves for their own communication purposes, we may be able to tap into that. So we are not looking into UFOs. We don't think so that UFOs are in fact aliens because there are other explanations for that. We call that, people in fact call them UAPs, right? Unidentified aerial phenomena. It's like we don't know what they are. I mean, and to associate them that they are alien is probably just too naive. I think there are other explanations for that which we have to think about.
Yeah, I think, yeah. And if you did detect aliens, would you be allowed to tell us, Vishal?
Sure.
Just to kind of add to the point of the previous question, one of the reasons people think we listen to radio waves is just not just the fact that we have a transistor, but also a lot of movies actually show it that way, right? Jodie Foster in Contact and some recent movies. So the kind of misleads people a bit. Can I ask HP to unmute and ask the question about ET? HP?
Yes, sir.
Yes, please go ahead.
Sir, if extraterrestrial life exists, is there a chance that there exists an exact copy of life as that on Earth?
Well, it is hard to say that whether there will be exact copy of Earth, because there are also hypotheses which suggest that life on Earth did not originate here. It came from somewhere else. Like the first seed of life basically was originated somewhere else, and then how it got transmuted to Earth, and then it kind of started here. So maybe biologically they may have some connect, if that hypothesis is true, by the way, assuming that, okay. If assuming that hypothesis is true, that life did not originate here, but it originated somewhere else, maybe there are biological similarities, but it's probably very unlikely that the other life form would have anything similar to us, because the way human or life on Earth has existed or has kind of come out to whatever form we see today is all due to its own natural environment. Like what is the best way for it to survive is nature environment. That's how it has progressed, and that's how it has survived to the level. And that's how the biodiversity that you see on Earth has kind of come to that level. It is unlikely that that will exist going to happen in another planet in an exact same fashion. So if we find life, it's probably going to be vastly different than what we are seeing on Earth. Maybe there will be some similarities. Like, for example, eyes. I mean, this is a very good example. Like on Earth, we have seen that eyes have kind of risen in evolution in 5 or 6 different ways. We're completely independent of each other. They have no really connection, but they all kind of came to the final way of like, how do we see light? Maybe then there are some similarities like that. Maybe aliens will have a similar ways of like receiving light, maybe other waveband. But it's very hard for us to speculate at this point.
I think a couple more questions left. Raghav Narasimha, would you like to unmute and ask your question about GMRT?
So, like, is GMRT used for SETI purposes?
Not right now, but we are trying to kind of build necessary hardware and software infrastructure so that we can use it.
Thanks. There's a question from Crispin.
No, it's yeah, simple. This can you tell about? Oh, sorry, it's echoing.
Sorry,
A wow signal? Can you tell about?
Oh, the wow signal. Sure. So I think it was like a while ago. Using an Ohio antennas, they detected this mysterious signal, which they deemed as a wow signal. In my opinion, I think that just got like a pretty large publicity, more than it deserved. Signal like that has been seen a number of times, but they can easily get ruled out. The reason is that anything that we see only once can never, and which we don't seem to repeat, are hard for us to scrutinize. So most of the signal we try to search, we expect the signal to be persistently present in the sky. If signal comes and goes, we have no way to verify whether that was what was it. That happened in case of the wow signal. That when one of the beam, it had two beams. When one of the beam detected this signal for some amount of time, but then it was vanished. It was never seemed to repeat. We never really detected anything like that. So it was mostly like some interference, which we were not able to distinguish at that point, but it is unlikely to be real.
Yeah. So the last question from YouTube, Aniket Prasad. He says he wants to study FRBs, especially its viability as artificial signals. Since you've been working on FRBs and SETI, would you like to say something about that?
Sure. I think when FRBs were first discovered, I think when first FRB was discovered, people in fact speculated that there could be a bright signal from alien civilization. But right now it is pretty straightforward for us to answer that there are not. The reason is that we have detected around 500 or 600 FRBs all over the sky. So unless there are 500, 600 ET who are doing exactly same and transmitting these signals, it is unlikely, which is obviously an unlikely scenario. I mean, simple Occam's razor suggests to that it is some kind of an astrophysical process which is producing these FRBs, not alien civilization, because there is no way that there are 500, 600 alien civilizations spread throughout the universe. I mean, first of all, we localize these FRBs to galaxies which are billions of light years away from us. So these, if you think that they are actually by alien civilization, why would they will be similar, even if the galaxies are spread like billions of years from each other? So billions of light years from each other. So it is unlikely. And obviously, a simple explanation is that there is an astrophysical processes which is giving rise to it. So FRBs are not ETI signals. But having said that, there are other classes of signal which are similar to FRBs, but they are distant in some ways. So FRBs have this, I'll take a minute. I'm sorry, Niraj, if that's okay.
Go ahead,
yeah. So in case of FRBs, what do you expect to detect are kind of signal like this. So what I'm plotting here, this is the frequency and this is time. FRBs exhibit this, what we call a dispersion delay, where the high frequency comes first and low frequency comes later. This is what we call a natural dispersion of FRB or pulsar, anything that you see in our in our universe. When they pass through the cold ionized medium of the galaxy, they have the dispersion curve. You can ask this question: what are the artificiality you can add to it? And then there are various ways by you can reverse this. You can have a signal. So this is again, time is increasing in this axis. You can have a signal which you receive at low frequency first, and then it progressively drifts to high frequency. Nature does not produce that kind of signal. Nature produces high to low. So if you see something that goes from low to high, that's an indication that is artificial. So that's where maybe there is a connection. You can see that by searching fast radio bursts, you can ask this question: what are the ways by which ETs can use this information and send a signal which can mimic, but there are some artificiality added to it that we can distinguish as an artificial signal. Like if ET sends a signal which looks like this, there is no way for us to know that that signal is FRB or that signal is by ET. right? So unless you have some artificiality added to it, we cannot distinguish it. So if it is smart enough, they might send a signal which has some added artificiality. And these are three different ways by which you can have artificiality. Like you can have low to high going this way, or maybe going this way. Nature doesn't produce these three kind of signals. Nature produces only this kind of signal. So if you search for them, all four of them, you may be able to do both. You may be able to do FRB, and then maybe you will to do the ATI. And that's what I guess I've been doing. I have a pipeline which does search for all these four kind of signals.
Thanks. Raghav has one more. We'll take two more questions, then we'll stop. Raghav's last question, would you like to read that aloud as well?
Yes, sir.
Say it aloud as well. Yeah.
Yes, sir. So, like, Govind Swarup sir actually published a paper on using GMRT to for SETI purposes. But why then GMRT is not yet used for SETI purpose yet?
Yeah, that's a good question. I think, it all depends on our interest and kind of resources that's available at the time. It is true that in 1992, when GMRT was sort of in its initial sort of building phase, Govind wrote two seminal papers which outlined that how GMRT can be beneficial for doing SETI experiment. I totally agree. GMRT should be doing SETI. That's what I am trying to do. It all depends on whether who is willing to take up that charge, who is willing to kind of do all the hard work, because it's not easy to do SETI. As I said, that the kind of signals we try to search in case of SETI are pretty peculiar, and you need to build the necessary hardware and software. There is a new interest with Breakthrough Listen. Breakthrough Listen is doing SETI across the globe. There is a new interest with GMRT as well, that it can still participate and it can do SETI. So hopefully we'll be able to kind of do that in near future.
Thanks, Vishal.
Can I take the last question?
There's one more question, and then maybe you could take yours, Sujat. Yeah. So the last but one question is on YouTube from M. Lagvi. There are bacteria found on Earth that can tolerate extreme temperatures, even more than 100 Celsius. Do you think such life can exist on hot stars like the sun?
I mean, hot stars are pretty hot then.
So maybe cooler stars. Yeah. Cooler stars in the sun.
Sure. Yeah, I'm not an expert on it. I think it's unlikely for life to exist on star per se, but yes, there are hot planets which are what we call tidally locked to their parent star, where temperatures go pretty high. If, for example, I guess you still need to have origin of life. You still need the life to get jump started. Once the life gets started, it may eventually be able to reach to a level where it can survive more and more harsh conditions. So my life might not have originated initially in the harsh condition. It might have originated in a very proper common place, but it evolved to survive in a harsher and harsher environment. If that is the case, then on these planets, if life somehow got started on some other parts of this, and then it kind of came down there, and then it survived and evolved to a level that it is able to sustain these extreme heat, then yes. But so far, we don't know much about it. So I'm not an expert on that. So I can't really answer whether life can survive. But so far, what I've kind of heard, it is unlikely for life to, at least the life we know it, to survive in such extreme conditions.
Thanks, Vishal. So the very last question goes to Sujan Sengupta.
Yes, Niruj, Vishal, it is an excellent talk. Lot of information. Learned a lot. The last question is, what is the future of the Breakthrough project?
Sorry?
Now 10 years project, so already almost 7 years are over.
Yes.
$100 million. So how much is left and where it is going towards?
Yeah, so I think we still have 3 more years to go. So we are obviously continuing our current effort. Breakthrough Listen is probably going to continue, hopefully, but I can't say for sure, because it all depends on what the Breakthrough Initiative, the advisory board, makes a decision on that. So far, the indications that what we could say is that there is a huge interest in the community to continue this. So what Breakthrough did is basically jumpstart the interest of SETI among the large community. And we are hoping that survives, even if the Breakthrough Listen itself does not exist. But Breakthrough Listen will exist in a form that what it has started. So when Breakthrough Listen started, it started with only 3 telescopes, with GBT, Parkes, and Automated Planet Finder. But right now, we are running the same program across maybe a dozen facilities. And that will still going on. Like that will keep go on even if like the initial breakthrough listen program, which was going on with these few fixed number of telescope, may not last for more than like 3 or 5 years. But beyond that, because there is a huge interest now, and then we have built a community of experts and people who are willing to basically do this work. And then there is a huge amount of sort of support that we get from Breakthrough Initiative that we can continue to do this for another decade or so. So I am hopeful for the future.
Thanks. So I think that's all the time we have for questions. So I think that, like Sujata, was a fantastic talk, and I hope all of you enjoyed it a lot. And we start off with a topic which was pure speculation for many decades, if not centuries. In fact, it was probably the ultimate existentialist question. And then Vishal told us about how it's now entered hardcore mainstream science, apply the scientific method to talk about getting signals from SETI, astrobiology, astrochemistry. So it's now in the domain of actual science, right? And that I think is a fantastic thing to happen. Before we end and we thank the speaker, I just want to say that there's going to be a complimentary talk by Sujan Sengupta tomorrow at 5:30, and the title of that is going to be why don't we receive signals from aliens. So Vishal told you how they've been trying to do that, and Sujan will tell you why we don't do that, right? With that, and then the same Zoom link and the YouTube link will be online. You can do the same Zoom link login. Also today, we're having if you are from Bangalore, we're having a multi-institutional panel discussion at 3 o'clock to talk about various opportunities for astronomy at every level, school teacher, school students, teachers, college, UG, PG, general public, etc. in Bangalore. So there's a very Bangalore specific focused event at 3 o'clock. And then at 6 o'clock, we're going to have another fantastic event where Professor Radhakrishnan, who's the ex-chairman of ISRO, with Sri Somanath, who's the current ISRO chair, will interact with Professor Annapurni Subramaniam, the director of IIA. And they'll be doing this from the Vainababu Observatory, from the Vainababu telescope floor in Kavlur, followed by a virtual tour of the telescope itself. So I do encourage you to join for that as well. Again, YouTube links are the common YouTube links, yeah. So the YouTube normal link would be just go to the YouTube page of IIA is there, and we have a bunch of programs tomorrow as well, ending with the public talk by Sujan Sengupta, like I said. So with that, let's thank Vishal, everybody, for a fantastic talk, a great talk to start the morning with. And thank all of you for coming and joining us both on YouTube and Zoom. We'll see you in our next programs today and tomorrow as well.